All right, how are you doing? Here is our equilibrium lesson. So let's imagine a chemical reaction. We'll take the simplest one where chemical A can become chemical B. And there are several of these types of reactions. Maybe the bonds are just breaking and rearranging in a different way, but there's nothing else colliding or it needs to happen. So at this point, we're used to chemical reactions going one way. A turns into B and then it's over. But in fact, a lot of reactions can also go in reverse. Once A becomes B, some of that B can also go back to becoming A. And this is known as a reversible reaction. And so these types of reactions, it's not like you have all the ingredients and then eventually you have all the products. You're going to have some reactants that are essentially always going to be there, like you're never going to completely get rid of the reactants. And this is where the concept of equilibrium comes in, is that each of these reactions doesn't necessarily have the same chance of happening. Like maybe one of these chemicals is more stable than another, so it's more likely to last, or there's something of that nature. So for example, let's say that in this reaction, every given second, A has a 30% chance of turning into B. So based on the energetics of it, if you're an A molecule, or whatever this may be, 30% of the time you're going to change into B. And let's say that in any given second, 10% of the time, if you're a B molecule, you will turn into A. And that is how the energy works for this particular scenario. So now let's look at some numbers. Let us say that we started with 10,000 A molecules and 0 B molecules. Remember, 30% chance of A becoming B and 10% of the opposite. So the first step's pretty easy to see. If 30% of A will become B, then 30% of that is 3,000, and you would expect there to be 3,000 B molecules. And since there were no B to begin with, none of those are going to turn back into A, and so you'll just have 7,000. Now the next step's a little trickier because 30% of the 7,000 will turn into B. So if we want to do that, take 30% of 7,000, which is 2,100. So that means B is going to increase by 2,100. However, we also then have to remember that B is turning back into A, and it's turning back into A at 10%. So even though B is gaining 2,100, it's losing 300 because some of that B is turning back into A. Now, I don't really want to do all this math out. I have a formula in here that will do it for me, which you don't have to worry about. We're kind of getting into the weeds a little bit. But you can see B increases by 1,800 because 2,100 came from A and then 300 was lost to B. And so we can keep this going step by step. And again, we're not really that interested in the math. I just want to look at the end result. Over time, eventually what happens is A is decreasing, and eventually we reach a point where the amount of A and B is relatively stable. And we call that equilibrium. And from our vantage point, it looks like the reaction ended, that the amount of A is constant and the amount of B is constant. But the reaction didn't actually stop. It's just that the amount that's turning into B and the amount that's turning into A is equivalent. So every second, the reaction is still going. It's just that it's reached what we call equilibrium, when the forward rate equals the reverse rate. And so that's one example where we started with 10,000 A and 0 B. What if we didn't start with this amount? What if we started with 5,000 of each? So again, without getting into the weeds too much, after 1 second, you would have 4,000 of A and 6,000 of B. And you can prove this, you can do the math out and improve that, but I'm not as interested in that idea. But let's just continue this for a good amount of time. And again, over time, the A is decreasing, the B is increasing, and eventually, again, I reach this point where 2,500 A and 7,500 B, where it's pretty much, it seems to be constant. Us as outsiders would look at this reaction and say, oh, it finished. But again, it didn't really finish, it's just that the rates are equal, and from our vantage point, it looks like nothing is changing. Again, this is what equilibrium is. Notice it's the exact same numbers as in the last time. We start with 10,000 total molecules. Here we also start with 10,000 total molecules, and the amounts ended up the same. Let's do one more of this type. So now if I start with 2,000 of A and 8,000 of B, so now I started off with more B. So, how's that going to change things? So we're going to let time pass and, do about 20 seconds worth of this. And again, A in this case, because there's so much more B, even though it only had a 10% chance of happening, so that means that, B, 800 of them are becoming A in the first second. And for A, we said 30%, so 30% of 200 is about 600, so 600 becoming B. So you can see A is actually increasing this at this point. So it's not always going to end up like the reaction's moving forward. In this case, it seems to be moving backwards, as it were. But again, if we go down and look, eventually we end up with the same amounts of A and B as if we started with any other point. So equilibrium, no matter what your starting conditions, you're always going to end up at the same sort of ending conditions. Now, let's not confuse this though. We're not going to always end up with 2,500 and 7,500. What it is the ratio. So the ratio of B to A is always going to be 3 to 1 if this is the energetics that we've established, if it's 30% and 10%. So B divided by A will be 3 in all these cases. Let's look at one more case where we don't have 10,000 total molecules to start. Here's a case where I had 14,000 of A and 10,000 of B. And let's let this run for the 20 seconds. And I let this go, and over time, eventually I hit 6,000 of A and 18,000 of B. Once again, 18,000 divided by 6,000 is 3, and this is how we measure equilibrium. It's the ratio of the products to the reactants when the reaction has appeared to end, when the forward rate equals the reverse rate. So hopefully this gives you an idea of why equilibrium occurs and how we sort of get there, and helps diminish that misconception that the reaction stops. Again, it's always going. It's just that the two rates balance each other out, essentially. So the reason this happens, again, is there's 18,000 of B at the end and 6,000 of A. Well, we said it was a 30% chance going forward. So when you have 6,000 A, 30% of that is 1,800. So 1,800 A are changing every time. And if I have 18,000 B, if 10% of those are changing, then 10% of that is 1,800. So every second, 1,800 A are turning into B, and 1,800 B are turning into A, hence why nothing appears to be changing. So again, that is what equilibrium actually is in this case. All right, so until next time, I am Derek Genova. Have a delightful day.